Hello and welcome to ABB Digital Transformation Podcast. I'm your host, Balqis Al-Daghar, an e-mobility specialist at ABB based in the UAE. We are bringing ABB global experts on board to share breakthrough digital technologies implemented on real cases in transportation across the world. Today's guest is Edgar Almeida, Senior Director, Digital Transformation and the author of the white paper, A Scalable, Flexible, Cost-Efficient Electrification Solution for EV Fleet Depots. This study is a joint study with UPS. So, without further ado, welcome, Eddie.
Thank you, Balqis.
So, Eddie, I would like to start by asking you to please introduce yourself and talk about more about your background.
Happy to do that. So I am actually pretty new at ABB, just about 2 years compared to what you will find at ABB, good 20, 30 year tenures out there. However, I've been in the industry for a very long time. I've been for the better part of 3 decades in some of the largest automation companies like Siemens, ABB, Schneider Electric, as well as I've spent a good amount of time in the IT industry with companies like Cisco, Verizon, and several Silicon Valley startups. I have a formal education in electronics and telecommunication and specializations in various software technologies thereafter. Spent a lot of time in the US and in Asia Pacific, doing roles in product management, technical pre-sales, business development, strategic partner management, and so on. Here at ABB, I lead solution architecture in the digital transformation group of ABB, and I'm based in San Jose, California.
That's great. So we are going to discuss your white paper today, and it strikes me, and it sounds a little bit more unique that we are focusing especially on EV fleet depots. So maybe that's where I want to start by asking, why did we start with fleet depots?
Yeah, that's a great question, Balqis. So our digital transformation group actually focuses on several key trends. Electrification of transportation was one of them. And we generated a point of view here that led us to focus on fleets. So, even prior to the COVID-19 crisis, there was already a steady increase in the need for last mile logistics. The way people have been shifting their buying trends to go online and do fulfillment through e-commerce platforms like Amazon and so on. Mind you, Amazon and e-commerce are still a very small portion of global trade, but that's growing at a tremendous rate. Now, this trend has only gotten more intense, in these COVID-19 times when you had to be staying at home and still need life to carry on. So I feel that people are getting used to this method of, procuring what they need, and this is here to stay even after the pandemic has passed us. Well, what enables all of these kinds of e-commerce deliveries to happen is fleets, and in particularly the logistic fleets. Now, while that's all good, that we have answers to, how is our material going to get to us, at the same time, there is this big focus on how do we decarbonize all of our establishments, our business establishments, transportation being one of the major contributors to the greenhouse gas emissions that impact our climate. So in this effort to decarbonize the transportation sector, logistics is a major contributor to this. And so we decided to focus on that subsector of logistics. Last mile logistics, particularly the trucks that reach your houses, etc., they are impacted pretty heavily. They impact the emissions pretty heavily through their diesel trucks. And mind you, they come into urban areas, right? They come into where places are pretty densely populated. Sometimes roads are pretty narrow and so on. So they have been brought under scrutiny by many of the city departments of transportation and emission control boards and so on. And they are the ones adopting the electric vehicle technology as the way to get around that. So those are some of the high-level thinkings that drove us to prioritize fleets, and in particularly logistics fleets, companies like UPS, etc., who understand that they have challenges and they need to overcome that by going electric.
It's surprising despite, the pandemic. It just seems like we have all the right reasons to push forward and to go fully electric. Um, Even though with all of this, all of these reasons, we still see barriers ahead of us to make the implementation or really go real. So in your paper, you have mentioned around 6 barriers that will slow down the transition. And just can you give us more thoughts on which of those you find most challenging to work around? Or often never thought of? Or do you think if one barrier is solved, the rest will easily come along?
That's a great question, and I wish the answer was the latter. But it's a pretty complex topic, and unfortunately, it's tied up with other things that are not related to just the technology of electric vehicles. So the barriers that we have highlighted in this paper are centered around the electrification aspect. Obviously, we are ABB, that's what we are known for, and so that's where we are focused. However, that's not to say that there may not be other barriers that the fleet operators have to deal with, such as, the cost of the vehicle is still high. It's of course coming at parity with the traditional internal combustion engine vehicles, and probably in a couple of years we'll be there at parity. It's mainly the cost of the battery that needs to come down, but also the unavailability of sufficient numbers of models from which to choose. So, for example, if you're running emergency vehicles or ambulances at the last mile, you'll want one kind of vehicle. If you've got delivery trucks, it's another kind of vehicle. If it's school buses, it's a third kind. And that kind of variety is just not rolling out off of the factory floors in the volumes that are needed by the industry. So that's one other kind of barrier that is there beyond, the electrical stuff. But let's come back to your specific question. So I would say on the electrical side, managing the cost of running this electrified fleet, right? And the cost comes from, the fuel cost, which is electricity that you're buying, as well as, making sure that when you do run these trucks with whatever the utility provides you as electric power, that electric power, by the way, has also got its own set of emissions, right? So it's got in California, it's almost 50%. The carbon emission factor is almost 50%. In other countries, it'll be higher or lower. So managing the cost means managing how you're consuming that grid supplied energy versus, let's say, putting solar on your warehouse rooftops and offsetting some of that dirty electricity with clean electricity that comes from your rooftops, or working through power purchase agreements with wind farms or other suppliers who are putting their energy over the grid so that you can be clean. So managing the cost, taking all these factors into consideration becomes an important thing. Now, at the heart of this problem is the complexity of the number of operational variables that you need to manage costs, right? The tariff structures are complex. In the United States itself, if you look at all the utilities, there are more than 50,000 tariff structures. Now imagine a company like UPS has 2,000 depots spread across the country. They span a whole bunch of different utilities that are supplying them. And you want to make a decision on which kind of vehicles to buy, what kind of route should I put that on. It's no small task to have all the math worked out. And these utility tariffs, Balkis, they are not a simple one rate kind of structure, right? They are different based on time of day. They are different based on season. There are critical peak periods, and so on and so forth. So that's a pretty complicated thing. So managing cost, right, is a big deal. Then there is obviously how your drivers drive those electric vehicles. In the case of our traditional diesel trucks, etc., it didn't matter how they drove, but in electric trucks, battery performance really matters, and whether you're charged, the amount of charge that you put in the truck before the truck goes out is sufficient, before they do all the deliveries and come back, and you've met your service level agreements. Will depend on how that driver is actually driving. Is he braking too much? Is he accelerating too much at the lights, and so on and so forth. So it's easy to overlook some of these other things, but I would say managing costs is one of the big things that I would say is at the heart of trying to solve for this problem of eliminating barriers.
Wow, there seems to be a lot of challenges. So we're not only looking at the electrical vehicles, we're also looking at the factors playing around it, like the stakeholders involved, also the facilities and the assets involved to the whole scenario. And so let's talk about the solution. You have mentioned really quite a lot of impressive details in your white paper about the architecture of the solution. So, what is a fleet grid?
Yeah, Balkis, and you said it right? So this is an architectural recommendation. ABB has, a wide variety of solutions from an electrical standpoint. We have the best products to create secondary substations from where you pull in power from your utility. We have, all of the electrical distribution protection equipment that comes after that. We've got charge poles that you can use to connect to your EVs and so on. So it's all about how do you put these things together. It's an architectural recommendation, and that's what the white paper was about. So kind of we look at a depot as or a facility in general, operating a fleet of EVs, almost as a little city or township, if you would, right? It's got many different buildings. They are supported by different electrical systems, for conveyors, for lighting, for water supply. I visited the UPS warehouse in San Diego on a hot day in June, and my God, it is hot in these warehouses where the packages are coming in and then being sorted and loaded into trucks and so on. So HVAC, or heating, ventilation, and air conditioning, as it's the full acronym for that, is a very important subsystem in there and consumes electricity too. As well as, like I was saying, the possibility of putting renewable generation through solar panels on these large warehouse rooftops. You're going to need backup generation, etc., to manage a fully electric fleet, right? So that's how we look at the depot, and that's what the architecture tries to address. So the variety of systems and their operating constraints, that will all vary based on the business. So at a shipping port, it will be different, at a bus depot, different, a factory. And in case of companies like UPS, which is a logistics distribution company, the requirements are different at their hubs. So these operating constraints, in turn, they place varying demands on how we build electrical systems and supply electricity to these trucks. So this complex interaction of electrical loads and the sources that are supplying this electricity, they directly impact the cost of running the facility, that means the energy cost, as well as the reliability of the operation. So, today, there is nothing unreliable about the fact that there is plenty of diesel stored in my underground storage area so that when my trucks come, I can pump it into them and off they go. Well, in a fully electric fleet scenario, now you've got to make sure that all of the network of electrical distribution, the transformers, the breakers, the chargers, and all that stuff is all functioning as reliably as that gallon of diesel that you had so easily pulled out from your sump, right? So that's what the architecture is about. So this architecture basically is an electrical system, and it's designed to be theoretically very flexible in its capabilities. It can address the gamut of interconnection, control, and management decisions that need to be made, sometimes on a minute-by-minute basis across the facility. And why do I say minute by minute? That's because, the way utilities measure how much power you are consuming in volume and how high that power level goes is calculated at minute level, right? There is this 15-minute bucket that they do calculations on. So if you want to be ahead of the problem, you better be making these decisions at really fine time slices, so that when the whole 15-minute interval has gone by, you have stayed within the limit of energy and power that was used to decide what they should be charging you. So that's why these things are this whole system has to work at that level of minute-by-minute calculations. So theoretically, we can scale this from very small installations that someone has got 5 electric vehicles to something as large as hundreds of vehicles, right? At UPS's depot, they had 260 vehicles at one spot. Overall, in their fleet, they've got more than 100,000 vehicles, but at this particular depot, there was about 260. Um, so, so the concept of this fleet grid architecture, it basically embodies intelligence that will automatically optimize energy use. It will maximize the resource and asset utilization that you've deployed on your site. It'll ensure that the most sustainable operating point for the site is arrived at. And when I say operating point, I mean, am I getting the right kind of charge time so that my vehicle can leave my depot at the right time once it is loaded and all other SLAs are met, as well as have I stayed under the CO2 budget that I had kept for this day of operation. So this solution and this architecture is aware not only of the internal site constraints, such as, what's the maximum power I can deliver from a charge point and what's the maximum power of this particular breaker at which it will trip, but it's also aware of the external grid and utility constraints and the factors in conditions on both sides of the meter, so front of the meter and behind the meter, while delivering this optimized site performance from an energy management and sustainability perspective. So from a logical system architecture standpoint, the fleet grid concept is built on this notion of three methods of aggregating and connecting all the energy system. There's a control plane from where all monitoring, optimization, and control is done. I actually, drew on a concept that is very popular in data networking. So the control plane is a notion I've drawn from there, and it applies very nicely here. The second is an energy plane. That's where all of the electrical power is flowing. So the atoms, the electrical, watts are flowing, the power conversion from DC to AC, AC to DC, depending on what kind of charging is needed and what source was generating the energy. So all that power flow is managed. And then an information plane, because this is a very digital solution, and we're making decisions all the time. So has to be a secure place from where information flows. And all the necessary data from internal and external systems is exchanged in a secure manner. There's role-based access control, so that only people with the right kind of authority can take action to change thresholds, etc., so that the system operates at the optimal level of efficiency.
Wow, that was quite detailed. I feel like we really did a dive deep in the architecture. And when you say that California is quite hot, I can completely relate to that, because here in the Middle East we do rely heavily on keeping our HVAC system on all the time. So I'm sure it was quite challenging, especially when you're looking at that depot with 260 number of cars which you are aiming to electrify. There are quite a lot of details and parameters in the architecture. I know we've done already some sort of a deep dive, but can you just pick a few of the parameters which you would like to highlight, and it plays a major role in orchestrating this whole architecture?
You bet. So before I get into the parameters that are managed by the solution, I want to tell you that there is a concept in this architecture called a multivariable optimizer. And a multivariable optimizer, as the word suggests, is basically a piece of software that's looking at a lot of variables. Some of this is just information that you have beforehand, like you can say, my charger can go up to 50 kilowatts peak. This particular battery storage system has 400 kilowatt hours of energy stored in it. So these are statics. And then there are some dynamic things that keep changing on a hourly basis or minute basis, such as, let's say, there are vehicles coming in to the truck, to the site at the end of their day, and they all come in with different states of charge in their batteries. So I need, when that particular vehicle comes in and connects, that's a variable the optimizer gets to see only at that time. And there are other things like, the temperature inside the warehouse because of a particularly hot day. Those are things that vary from, time to time. And so those are the variables. So there's static data and this variable data. And this optimizer is constantly looking at all of this and basically doing calculations and determining what it should instruct the equipment to do as a result of its calculation, so that the outcome is that your vehicles are charged in time, as well as you stayed below dangerous thresholds of power consumption that could end up bringing penalties on your electric bill, as well as meeting some of your carbon emission goals. So that's the big picture. That's what the optimizer does. So what kind of parameters does it manage? So you can look at them as two groups: input parameters and output parameters. So for example, input parameters could be the site manager's goals, right? It could be, let's say, the holiday season, Christmas, they're expecting a lot of deliveries. Site manager says, for this week, I'm not going to worry about, let's say, CO2 emissions. What I'm going to worry about is full charge for my vehicles within the window I've given that's available when the truck comes back. So, charge at the maximum power you can, because the truck has to leave with full charge by this time. That's an example of a site manager's goal. So that's one kind of input. As well as, the other inputs are things like the tariff structures of the utility, as I said before. They can vary by hour, they can vary by day, they can vary by time of year. So that's all a part of the inputs. The performance limits of the different equipment, right? So let's say if I have a backup generator that's going to be coming in, what is the load characteristic of this generator, right? It performs well at 50% load, it performs even better at 80% load. So I should always try to bring it up at that point. So that's another example of an input. So the capabilities of the assets is another example of the input. Then there are the outputs, and in the outputs, things are what the optimizer is telling the assets to do. So the output could be a recommended sequence of vehicle charging. So you can imagine, Balkis, at 4:30 in the evening, between 4:30 and 7, vehicles are coming back after their delivery routes. They could be 2 or 3 different sizes of vehicles. They had different routes. They carried different amount of payload. So they're all coming back with different states of charge. But then there is also a plan for the next day on what they should be doing. So depending on how they came back and what the state of charge is and what's their vocation for tomorrow, the optimizer will do a calculation and recommend a sequence in which you charge these vehicles, so that the right amount of charge goes into the right vehicle in order for it to accomplish its service level the next day. So that's an example of an output. The operating state of backup generation. Should I be firing up backup generation now or not? The activation of energy storage is an example of an output variable. Should I be drawing power out of that stationary battery that I was collecting solar energy from during the day or not? How do I adjust the temperature set point of HVAC so that I'm keeping my workers safe and comfortable, but I'm not jeopardizing the amount of power I'm consuming to charge my vehicles, so that I can optimize that. Those are examples of the outputs. Now, depending on the size of the fleet operation at the site, as well as the number of sites. And why do I say number of sites? I want to emphasize here that this architectural concept of ours is not limited to only what happens in one site. Several of these logistics companies have distribution sites that are all within a certain area, and they basically fall under one utility. And so imagine if we can optimize not just within a site, but across sites too. That means I say, okay, I'm going to make sure that all these 6 sites that are within California supplied by PG&E operate and consume no more than this much power in total, and generate no more than this much carbon emissions. So the optimization really allows for that kind of cross-site optimization also. And so your question about how many parameters could there be, theoretically the number of parameters can be in the thousands, right? If you just look at a single battery, a single battery in an EV could have 5 or 6 key parameters that we need to keep an eye on. Now imagine you've got 200 vehicles. You are already crossed 1,000 variables. Add to that all the parameters from HVAC and from the grid and from your solar installation and whatnot, and you can see that it is very easy for these numbers to be pretty high. all these parameters need to be processed on a minute-by-minute basis. Realize that. So that optimizer is a really fast system running on some pretty strong hardware. Uh, and kind of that's the picture, if you would, on parameters and the number of parameters that are processed in the Fleetwood architecture.
This is very interesting. I like how the optimizer acts more like a maestro. We are going way much deeper into defining parameters, but also all the way to decision making. I find this quite fascinating. And, the fact that the parameters can actually, range to thousands, that's a massive amount of data we're dealing with. And the nice thing you mentioned about also it's not limited to one location. You can scale it up to several other locations, and I can imagine this could probably go across cities, countries, or even continents. So it's quite massive, and it's really interesting. So from all of this, all of these details, can you bring out the key value or the value propositions that this solution architecture and concept can provide to our customers?
Absolutely. So the white paper lays out in great detail, the spectrum of value propositions. However, I'll kind of just talk a few that stand out as unique. So one is that the architecture affords the customer a data-driven planning methodology. So the fact that things are organized in this way, and we have the control plane and the energy plane and the data plane, you can envision a set of tools that allows the customer to do what-if scenarios. They'll say, what if I had 5 trucks with these specifications, 15 trucks with those specifications? What if I was operating them on these 2 shifts, and this was the start time and that was the end time? What if I had this much of solar panels installed on my roof? And what if I had this much of stationary battery storage to collect that thing? How would my electric bill and my CO2 emission look at the end of that? And then the optimizer would kind of run off and do its thing. So the first thing is that in this journey, these customers want to have good planning tools, right? This is all new, so there is no formula to follow. We've had 200 years of diesel vehicles, and that's a very well understood industry, but electric vehicles are just emerging, and so there's just nothing but questions all over the place. So that's one of the first value propositions, that we give them a way to do planning and make the right decisions as they are incrementally adding more electric trucks to their fleet. Then there is the main job of the optimizer, which is finding the lowest cost point for operating the whole infrastructure while meeting the business SLAs. So this is what you call the orchestrator, or the central brains of the whole thing. And so being able to find that lowest cost operating model would not have been possible by a site manager, sitting and doing calculations every time the trucks are coming back. I mean, I've been at these sites, and let me tell you that site manager's job is very busy. He is running around all the time trying to figure out, some question that some guy loading packages on some conveyor belt out there has, or some motor has stopped and the whole line is affected. And he's running by the seat of his pants trying to put out fires all over the place. So he's definitely not going to be the guy who's going to be able to figure out what kind of charging plan makes sense in this hour on this day. So the system is able to give them the lowest cost operating model. That's another key value proposition. And then a corollary to that is the fact that it also is doing calculations on the carbon footprint of the operation on any given day, right? Because you remember in your previous question, we said there are inputs. One of those inputs is the carbon emission factor of power coming from the grid. So the optimizer can make decisions like, okay, I'm getting cheap power, but it's dirty at this time of the day, and I have plenty of power stored in my batteries. If I want my overall CO2 footprint to be within a certain limit, I better not take grid power and use this power now, and I'll use grid power when it is cleaner. Remember, grid power can be clean or dirty based on time of day and seasonality. So solar energy obviously being clean, available during the day, wind energy being available in certain seasons makes the grid power that much more cleaner, and so on. So there's all those factors. The utility supplies you that clean energy factor number of its supplied model. So being able to run the depot in a more sustainable way, that's the corollary to the lowest cost operating model and a key value proposition. Then the fact that the solution allows a lot of scalability and flexibility in growing. So you don't have to invest in a whole bunch of new smart electrical infrastructure and software on day one. What we have learned from talking with companies like UPS, who have more than 100,000 vehicles, is that those vehicles have been bought at different times as the company has grown over the years, and they retire at different times, and they have calculations, financial calculations based on the residual value of the truck and so on. So they cannot just say, okay, whoa, there's some really nice electric truck that Tesla has brought out. Let's retire our current diesel trucks and get that. Well, they can't do that until it's time to retire those guys based on the asset value on the books and whatnot. So since they're doing this conversion in phases and gradually, sometimes it will happen over 5 and 10 years before the whole fleet is converted, it is important that the solution also has that kind of flexibility and can scale and grow with the customer so that they're not over spending and investing in the beginning. And then, so that's another key value proposition. And the last one I'd like to highlight is who's supplying these depots with power. It's the utilities, right? And until yesterday, the utilities knew what they were dealing with. They said, okay, there's this depot. The guy has all these conveyor systems and so on. He needs 2 megawatt of power, some lighting, some HVAC. I know what the guy needs. Accordingly, I'm going to plan my feeder line to his site, and my substation will be sized accordingly, and I'm going to make sure that the distribution, the transmission company knows how much power I'm going to pull from the grid, etc., etc. Life is good. When these EVs come, sometimes each of these EVs consumes as much power as the whole house, just one vehicle. And now imagine you put 200 of those in a depot, right? It's like literally creating a whole new block in the city. And now the utility has to deal with that. So the way these depots and the fleet companies adjust their energy consumption posture, as I call it, that means how they consume power from the grid in a manner that the grid is happy with, right? So don't just bring 200 trucks and connect them all at the same time and overload my feeder, because I can't deal with that. Do it in a way that you can, manage that charge curve by having schedules for each of the trucks and use your own power when you can, so that I don't have to do very expensive upgrades to my substation and feeders in order to service this sudden surge of electric trucks that you have at your depot. So that's the energy consumption posture, and this solution architecture of ours allows these depots to kind of present that posture, which really makes utilities happy with the situation and will actually be an ally of them as they are trying to look for permits to electrify their depots.
Interesting. So many great insights and really definitely great values for the customers. I like how we're going, a step ahead of just looking at cost, but also how sustainable the operation is, and the fact that it really puts in consideration how slow the transition is, and the affected parties on both sides, not just the consumer, but also the producers and the utility companies. Quite a lot of values there. So let's take all of that to implementation. So in your paper, you have done analysis on one of UPS fleet depots. Before we get into the results, can you tell us what was the case like before UPS thought about, electrifying their fleet?
Sure. By the way, UPS is among one of those companies in the logistics space that is really a pioneer. They have I think last I read more than 9,000 or 10,000 alternate fuel vehicles, in pilots and in operation at different parts of their business around the world. And they're constantly evaluating how they can transition out of these dirty fossil fuel-based vehicles to cleaner alternatives. Electric, of course, is one of those alternatives, but even natural gas is a cleaner option than diesel. So they've been doing that for some time. However, at the San Diego site, which is the place where we did our joint study, they only have diesel trucks, right? So they have a mix of these big rigs, the long ones that are running across the state, and if someone from Arizona is shipping something to someone in Massachusetts, obviously that's not being done by the last mile delivery truck. Those kinds of packages are aggregated, they're put onto these long haul trucks, and then they're taken to the next logical distribution point from when they are desorted and then loaded out onto distribution trucks. So there's those heavy duty trucks that do depot to depot kind of movement, and they have medium duty trucks that are doing depot to consumer kind of distribution. They operated a 6-day shift. They still operate a 6-day shift, 6-day week, and there's one shift. Vehicles kind of get out of the depot in the morning. They go to the distribution, picking up other packages that need to come back for sorting and grouping, and they're back like in the evening around 4:30. Then they are washed, refueled. All the sorting of the parcels are happening throughout the night, and then by the morning, all the trucks are ready for taking their next load and going off for distribution or depot to depot work. That's how they do it. There's literally 5 stories of conveyor belts in that warehouse that I've visited. You feel like you're in the intestines of some big mechanical monster. There's more than 400 motors running sections of conveyors that connect to each other. And there are diverters along the way, and it's a pretty complex operation. Now, all these loads that they have, these motors and other such equipment, they can be made very efficient with the right kind of electrical equipment controlling them, like using drives and other control technologies that could be orchestrated by what we have referred to as our optimizers. So it's very, very, it's a situation that's ready for us to bring in a fleet grid kind of architecture once the trucks join the rest of the characters in this electrical, let's call it a kind of dance out there. So in a post-EV implementation scenario, there will be a lot of these kinds of electrical systems to be managed. In peak season, this particular site could process about 120,000 packages in a day, and people work really hard during those times, the conveyor belts and the people. They are serviced by the local utility, who's San Diego Gas and Electric. And, as I was saying before, across the United States, there are various kinds of tariff structures. San Diego Gas and Electric has its own variety, where they have time of use rates, they have seasonal rates, and so on. Let's see what else is unique about them. So all of these tariff characteristics that are presented to the site can be, in fact, is quite a daunting challenge to them as they think about how they're going to transition next from where they are today into an EV operation in such a way that they don't, exceed their operating budget. These companies work on a operating budget of, how many cents do I spend per mile of service delivered, right? So that is their metric, and that should not change whether they're running electric or diesel. So they'll need to manage all of that. So yeah, so from a where they are today standpoint, that's the picture, Balkis.
Yeah, they must have been struggling in terms of, okay, where do we start and who should we reach out to? Which brings me to the question, how did we, ABB, get involved in this case?
Yeah, so great question. And, hats off to our previous CEO and our Chief Digitalization Officer who kind of got ABB started off on our digitalization journey somewhere in 2016. So that strategy really was a very well-rounded one. It didn't only focus on technology, it didn't only focus on skills, but many other things. So one pillar of that digital strategy was establishing a digital transformation consulting group. And this is a global group with consultants spread across the different parts of the world and made up of some very seasoned industry professionals. They came from, the energy and utility industry, from automation companies, IT companies, mobility, manufacturing, et cetera, et cetera. We even had a few people with telecom backgrounds and smart city backgrounds in the team. And the reason we had this group was that this group has the credibility to go in front of customers, and this group pursues customer engagements that have a digital transformation ambition. So in this case with UPS, electrification of transportation was the ambition of the company. It also was one of the main threads in which the ABB Digital Transformation Group had developed cutting-edge industry insights and points of view. By talking to several industry players, we talked to auto manufacturers, fleet operators, utilities, etc., and developed this very unique body of knowledge that we could bring to the transportation sector. So, having these assets and having this mandate, we talked to several companies. UPS, we found, was one of those companies that was ready to kind of move with us. They were already, like I said before, a leader in exploring decarbonization strategies in transportation, and we found a perfect partner in them. And they were honestly still waiting for their first wave of electric trucks to come into that depot in San Diego. They were expecting 32 of them to come there. This was all the way in the middle and early part of 2019 is when they were expecting them. However, we were kind of ready to demonstrate our solution, and so we agreed to kind of do a simulation. And by that, I mean we take real data of their current energy consumption. So we looked at all the utility bills for the last 3 years. How do they operate at every 15-minute interval of every day of the whole year? We had that picture with us. We had the information about all their current loads, their motors, their HVAC systems, their lighting systems, etc. And we had specifications of the trucks they were expecting to bring in. So these 32 medium-duty trucks. And we said, assuming that you have a solution architecture like this, and the optimizer being the center of that, able to do all this orchestration, how can we manage the charging of all these 32 vehicles and still give you the lowest cost outcome and the lowest CO2 footprint outcome as you're running your business? That was the objective of the simulation. So as the output of the simulation, we kind of told them that if you had no self-generated solar, no battery storage, no smart chargers, and you wanted to have these 32 trucks ready for service every morning, this is how your bill would look and what it would cost you. What if you had a little more storage of your own, electric storage, and if you had some solar on the roof? How would that change? What would happen if you participated in the utilities demand response program? What kind of rate offsets will you get? What would happen during critical peak periods, and how could you avoid getting penalized during those times? That was all the scope of the simulation, right? So what we did is we kind of created a well-structured engagement document, like a memorandum of understanding, on what we would want as support from them during this simulation and what would be the output from us at the end of the simulation. And we kind of embarked on that and completed the analysis and provided them that data, which was really well appreciated by their head of electrification and procurement, and gave them a really good understanding of how they should move forward with gradually selecting and transforming the vehicle mix in their fleet.
That's quite a really nice story, because I see that what really had us searching for each other, let's say UPS searching for a partner that has a common vision, is really the common vision. That we are, as ABB, we are trying to go towards a a zero emission future, and the fact that UPS are a leader in decarbonization, it just seems to me that that's how we ended up, of finding a common ground to work together. And what I find fascinating from implementing the solution architecture is that it comes up with several scenarios. And in your white paper, there were like 30 scenarios. What I find fascinating in that is that it shows you, it indicates the amount of savings on electricity bill and also the return of investment in a really impressive short time. So there's a lot of, data, or let's say modeling available for any customer when they look at these many scenarios. It's very easy for them to make a decision on how do they want to start, and I find that really fascinating. I want to take you to the next question. What do you think would be at stake financially and otherwise for UPS if it did not undertake a comprehensive scenario assessment like they did with ABB based on the fleet grid solution architecture concept?
Yeah, thanks, Balkis. And that's really the key question, right? Why did they take the trouble to work with us? Excuse me. What we were offering them was a way to mitigate risk as they embarked on this journey of electrification, which they were at the leading edge of, right? There aren't too many people they can follow, so they've got to be the path breakers, and obviously in the process they need to make as little mistakes as possible. So I would say I would group the risks that we help them manage into the following buckets. They could have made, without a system like this, they could make the wrong choice of which vehicle model to choose for the particular, vocation. Let's say one guy is doing long haul, hub to hub. One guy is doing last mile, but he has a very busy last mile network, whereas another truck has a not so busy last mile network. Even the terrain, right? Am I going uphill and downhill all the time, or am I delivering parcels in a terrain that is relatively flat? Even that makes a difference in what kind of battery size you would need, or what should be the state of charge of your vehicle, or sometimes even what kind of model of vehicle makes sense to purchase. So if you don't have a way to simulate the different kinds of vehicle models and see what the cost and CO2 outcome is, you could make the wrong choices. So that's one of the risk buckets that this kind of an approach helps to mitigate. The other thing is on the electrical infrastructure. So you're heading towards 200 trucks, right? Does that mean you build the transformer right now for dealing with the power that would be needed by 200 trucks? What are your alternatives? How can I spend my money on electrical infrastructure so that I'm not oversizing everything? Mind you, when you oversize equipment, you always impact efficiency, because there's always a certain amount of waste that happens because of the size of the equipment, right? Imagine trying to kill a mosquito with a cannon, right? Obviously, you're wasting way too much energy than what a fly swatter would have worked for. So that's basically what it is right sizing the whole end-to-end electrical infrastructure so that you don't end up having to pass through all these expensive costs to your consumers. At the same way with the utilities, if you say, hey, I want 6 megawatt of power. Yesterday I had 2 megawatt, but I'm bringing 200 trucks and I need a 6 megawatt feeder. Well, they're going to look at it and say, at the mileage of a feeder that I need to upgrade to you is going to cost you millions. Are you willing to spend that money now and put that, or can you work with a smarter way in which you do your charging so that I don't have to upgrade these feeders and I don't have to upgrade my substation, etc. Right? So that's the aspect of right sizing, and that's another risk that is at stake and something that needs to be managed. And then the inability of the business to reach sustainability goals at the lowest, cost of operation, while still delivering on SLAs. Today, more and more businesses have to, put out their performance in sustainability terms on their annual reports and so on, and customers are literally making choices on who they'll go with depending on what kind of track record you're showing in your sustainability. So those are some of the key things that were at stake, I would say, Balkis, for which our solution architecture was kind of constructed as a way to help these companies solve for those risks.
Interesting. I wouldn't want to be in their place if I would face all of that. Definitely reaching out to experts and people who are experienced and for a very long time in this field is key to accelerate the full electrification of fleets. Given that this, electrification of the automotive sector is really new, complex, and it's evolving. What are some of the other likely factors that will impact the adoption rate and strategies of EVs?
That's a very pertinent question and very multifaceted problem, actually. So EVs are part of what I call the perfect storm that is brewing in the transformation in the electric grid sector. EVs represent obviously the largest potential growth in a new load class for utilities, and they want to see load growth because that's where they get their money from. But these vehicles also present a great end system, with their large energy storage characteristics, the car battery. They could be a new and a new kind of way in which the grid could get help to be resilient in the face of a really exploding penetration of renewables. So what's the connection? Renewables are a source of clean power, but they also come with their own challenge of being notoriously variable and unpredictable in the amount of power they produce. The grid is not designed for that kind of unpredictability. The grid is actually designed for a very predictable generation paradigm and consumption paradigm. I'm not saying that's the best way to build a grid, but that's the way we've ended up with our grid. So batteries act as this kind of sponge in the network where if there is too much power generated, it can be stored and doesn't have to be curtailed or done something less optimal with. And when the load has increased for some reason because of a very hot day and there isn't enough traditional power to be generated from the generation plants, you can pull power out from these storage systems, these batteries, and support the grid. So the grid needs support both on the excess generation as well as the excess consumption side of things. And this population of electric vehicle batteries connected to the grid at any time can act as a grid buffer against these over and under generation behaviors. So that is one kind of complexity that is part of this whole equation. So the grid must evolve to be a smarter transactive entity versus its traditional form of being a one-way pipe from generation to consumption. In the past, several industries like telecom, media, banking, and finance, etc., that operated more or less like this one-way pipe, all of them have transformed by using digital to become bidirectional transactive systems. And in the process, they've unlocked a ton of value for everyone across the board, for all stakeholders. In the same way, the evolution of the electric grid and the whole electrification of transportation will be, going through this dance, and it will be, and how they work together will be one of the major factors that will impact the adoption of EVs. The other phenomena that will impact adoption of EVs is related to the total cost of ownership of EVs, right? Obviously, you want as small a TCO as possible. Today, their initial cost of acquisition is high because of the cost of batteries. However, the subsequent cost of energy and finally the residual value of the vehicle when it is past its first life into what we call as the second life are also important metrics to keep an eye on, as they impact TCO and therefore will impact the uptake of adoption rate of EVs. We will only be able to master these metrics over time when there are enough EVs on the road and enough production experience and enough penetration of vehicles into the market. Good news is that the learning rate of the industry as a whole, the EV industry, is very encouraging, and I think we'll get there. On the operational side of things, vehicle range, how far a vehicle can go with a certain amount of charge, as well as the availability of sufficient charging infrastructure, both the level 2 slow charging or AC charging as we call it, as well as the DC fast charging, both those infrastructures. So those are key factors, and people need to be comfortable that there is enough range and enough availability of charging infrastructure in order to adopt EVs. Mind you, depots don't have this problem because since they are operating in a depot-to-depot manner, they are masters of their own destiny. They can build the necessary infrastructure they want on site in terms of chargers, etc., and select the right kind of vehicle batteries so that they can get the range they want. Lastly, and probably over the looking kind of crystal ball gazing out here 10 years into the future, the impact of alternative decarbonization strategies in transportation could impact the adoption of EVs. What do I mean by that? I mean, the rise of hydrogen-based fuel cell vehicles, which are electric vehicles, but they don't use batteries. They basically have hydrogen as the fuel source, which is a pretty clean energy carrier, and that could kind of impact the way the traditional battery electric vehicle future will form out. Also, the shared mobility business model, as well as the autonomous revolution that's happening, all of them are going to change how people buy mobility services. Are they going to buy their own vehicle and move things, or they're going to rely on some other shared or autonomous service to do that? And that will in turn affect how this whole breed of EVs comes to be in the market. So I think the customer should always have the tools to make the right decisions, data-driven decisions, as they move forward in changing their transportation strategy into a low-carbon one. But more or less, I think from my point of view, those are some of the other factors that will impact the adoption of battery electric vehicles.
Interesting. And I think, despite all of these factors, I still see that the market insists on moving forward, because definitely the future is electric, and not only that, but it's also autonomous. So I'm interested to know about what is happening with UPS today, despite all of that. And did they start with their second phase already? And if they did, what does it look like?
Yeah, Balkis, I wish I had a better story to say out here. And as I had mentioned before, electrification-related aspects are not the only barrier that these, brave customers who want to go low carbon have to contend with. Just the availability of the right kind of EV models to suit their use cases, is a problem. And the case of UPS, that has been one of their challenges, that there've been a lot of delays in getting the electric trucks, the medium-duty electric trucks that they had ordered. It's not that the company did not produce them, but the way it's done is that, you make a model prototype, then you do your testing for the particular vocation. So UPS would be the guy that would put it through through the grind. And in that process, a lot of feedback goes to the company, this doesn't work right, that needs to change, and so on and so forth. So that cycle has been slow. And as a result, they have not yet managed to get the quality of those trucks that they need from their supplier. Even as of today, at the time of recording this podcast, they have still not received them. They're expected shortly, maybe in the first half of next year, because of the COVID delay again in the middle. But that's their situation. However, I'm confident that UPS has absolutely the right perspective and ambition and the right approach. And, with a partner like ABB, they can definitely move into large-scale implementation of EVs in their fleets as soon as this supply problem is resolved.
Well, despite all the challenges, I think I'm very optimistic about the future, and I want to thank you, Eddie, for this deep knowledge and rich experience that you have shared with us. So we have reached the end of the podcast. So I would like to close with the podcast with you, Eddie. Maybe you can give us a closing note before you leave.
Yeah, it's been an absolute pleasure on this topic, Balkis. Thank you for inviting me. I am just super excited about the future of the whole energy transition. It's exciting. It is sensible. It's the right thing to do, and in the process, it is making all of us think creatively, and is actually, creating a whole new set of industries and jobs. And I'm really happy for that. So, yep, let's stay with our uh, foot on the accelerator in this journey and change the world and make it a better place.
I couldn't agree more. Thank you, Eddie.
You bet. Have a great day. Bye now.
Thank you all for tuning in to this podcast. We're happy to hear your suggestion. Please reach us out. So this was your host, Belqis Al-Daghar, and that's it for today. Stay tuned for the next episode.